my colleagues. As mentioned, the topic of our research is frame size optimization using machine learning approach in downlink MIMO channel. These are the contents of the presentation: introduction, literatures, a statement of the problem, objectives, significance of the study, proposed approach, results and discussion, and finally conclusion in which our work will be presented. As an introduction, as you know, the usage of neural network, wireless network is increasing, so that improving the performance of WLAN has becoming as an important and challenging research topic, even if the technology is increasing. So the performance of WLAN depends on several parameters, such as modulation, coding schemes, contention window size, retry limits, frame size, etc. So optimizing this parameter would improve the system performance. Among these parameters, frame size optimization is one of the most important factors that would affect the throughput of WLAN. The IEE standard introduced different technologies. One of these is frame aggregation technology to accommodate the growing traffic demand and increase the performance of transmission efficiency and channel neutralization by allowing many packets to be aggregated for transmission to improve the throughput of WLAN. However, if the frame size is very large, the bit error rates will destroy the whole frame, thus the frame success rate will be decreased and the throughput degraded. On the other hand, if the frame size is very small, the overhead transmission such as the MAC and physical headers, acknowledgement, those things would occupy the large portion of the transmission, thus reduces the efficiency. Therefore, deciding the optimal frame size is critical to the throughput of WLAN. So when we come to the main focus of this research, the problem, the difficulty, the benefit of utilizing frame aggregation in downlink MIMO channel is it's not efficient, it's not effective, because of the stations in downlink MIMO channel, as you see in the diagram, have heterogeneous traffic demand and transmission rate, which causes wasted space channel failure, and that degrade the transmission efficiency. So the different approach proposed, the adaptive aggregation approach, is significant to realize optimal frame size that, as per the conditional traffic pattern, channel conditions, that would maximize the system performance. So in response to the performance demand of today's network, machine learning approach is a significant approach, increasingly used in different field of studies, and of course in the context of wireless communications, to generate a self-driven network that can configure and optimize themselves by reducing human intervention. Moreover, ML approach or machine learning approach provide an advanced approach that can autonomously extract patterns and predict trends based on the environmental measurements and performance indicator as an input. If we see some of the literatures regarding frame aggregation, first we can see frame aggregation works previously done without MIMO technology. If we see benches proposed studied the relationship between throughput and frame size, and he emphasized that the larger the frame size, the better the throughput. But the limitation in this work was he does not consider the issue of transmission error, so which is unrealistic result. So the other one, the other person is proposed in on the paper 30. By the way, these research are found on the paper as well, but I try to list some of the literatures at the bottom. So machine learning based frame size optimization approach in considering channel condition and contention effect of users is proposed by this person. According to their simulation result, they can able to optimize the frame size effectively to achieve the maximum throughput performance of WLAN. However, the limitation of this work was it does not support frame aggregation mechanism and is not suitable to apply on MIMO-enabled WLAN. The other literatures concerning on frame aggregation schemes in MIMO channel. There are few studies which are conducted on this topic on MIMO channel, frame size aggregation schemes. If we see the 15s on the paper, they propose a dynamic adaptive aggregation scheme to determine optimal length of frame size in downlink MIMO channel. So in this case, they consider heterogeneous traffic demand among streams. However, they do not consider transmission error. They assume ideal channel time. So they contribute maximum performance of system throughput performance and channel utilization. Basically, this work is our previous work. And the second one, work in 16, is also our previous work. This is Scopus indexed, and 16 is SSI indexed journal, our previous work. So in 16, the work in 16 extends the limitation on the paper 15, which does not consider transmission error, but this one considered transmission error to provide, to enhance adaptive aggregation strategy in 50. The data, again, the data frame construction scheme called DFSC is also proposed to find the length of MIMO frame, aiming to maximize the transmission efficiency by considering the status of the buffer and transmission rate of station in both uplink and downlink multi-user transmission. However, these three approaches do not consider a machine learning optimization solution, basically. The fifth one as well do not consider, the seventh paper and the 17th one do not elaborated frame aggregation strategies, and channel error is not considered as well. And then the experiment is not examined under the effect of different traffic models. The other one is frame size based aggregation scheme is also proposed to resolve the problem of these heterogeneous traffic effects on the performance of throughput in MIMO channel. This approach considers frame size based aggregation scheme. The idea here is by making all frame size, by making equal the length of the frame size in all spatial streams, we can able to they propose to maximize, they intended to maximize the system throughput performance of WLAN. However, under the actual scenario of heterogeneous traffic demand in different spatial streams in MIMO channel, it's not feasible to always make equal frame size in all streams. So this approach also does not consider channel error and is not examined under different traffic scenarios. 19th also proposed a novel method to determine frame aggregation in downlink MIMO channel to improve channel utilization considering delay. The difference between the main idea, the main contribution of this paper is to improve channel utilization. Again, aggregation aggregation scenario is not elaborated, and the issue of channel error is not considered. So that was a limitation on this paper as well. So some studies focus on padding problem. According to this 2%, 2021, they improved the transmission efficiency in downlink MIMO channel by replacing padding bits. By replacing the space, which means padding bits is added at the end of the shortest frames in downlink MIMO channel to avoid the space. But these padding bits doesn't have any meaningful information. Just this is added to make it equal the transmission duration of all streams of on the channel. So this degrades the transmission efficiency. So that this approach by replacing padding bit with frames from other users, they try to avoid space channel time and increase transmission efficiency. However, this approach completely violates the rule of MIMO transmission, which requires modification of the standard. So other literatures also conducted frame duration-based frame aggregation. So this approach, the main approach of this work was by providing high priority to mobile station, expecting high throughputs and MIMO channel, they select the stations. So they try to equalize the transmission time of all spatial stream in all MIMO, or in all mobile station according to the modulation scheme level. They achieve the maximum performance and minimize space channel. So the main contribution of this paper is to maximize system throughput performance of WLAN, minimizing space channel time. The limitation of this approach is this approach always prioritize station with expecting high throughput in the system station. So they select station with high throughput. So the experiment is not evaluated under different channel conditions as well. So in general, from the literatures we try to mention above, all the above proposal contribution, several schemes to enhance the performance of WLAN. However, none of the above the earlier approaches do not consider machine learning-based optimization solution. So the statement of the problem is the advantage of frame aggregation MIMO transmission is not always achievable due to heterogeneous traffic demand among spatial streams, which results for wasted space channel time. As a result, utilizing specific aggregation policy may not be optimal in all channel conditions in traffic pattern. Most of the existing aggregation approach in WMIMO channel are not adaptive under the effect of unpredicted traffic patterns and channel conditions to determine optimal wireless frame setting. Machine learning approach is the recent innovating solution to maintain self-driven networks that can configure and optimize themselves by reducing human intervention that has been shown to be capable of overcoming the drawback of traditional mathematical formulation and complex data analysis algorithms. However, most of the existing approaches do not consider machine learning-based optimization solution. So the objective of this paper is, the main objective is to enhance the performance of WLAN by optimizing the system frame size that would maximize the system throughput in downlink MIMO channel in considering the effect of channel condition, heterogeneous traffic pattern, and number of stations. So this is to achieve, and also to achieve machine learning-based adaptation approach for frame size optimization, which is capable to autonomically extract patterns and predict trends based on environmental measurement and performance indicators as an input. So the significance of the study, the proposed approach has significant potential to improve the performance of WLAN by optimizing the system frame size and tackling the issue of heterogeneous traffic demands among the streams, channel conditions, number of stations in the MIMO channel. Machine learning-based optimization solution is adopted in the proposed approach, can provide a self-driven network that can configure and optimize itself by reducing human intervention. Moreover, the capability of overcoming the drawback of traditional mathematical formulation in complex data analysis will not be is achieved by adopting the ML approach in this study. So the proposed approach, this approach, the simulation environment proposed by our previous work, as I mentioned so far, 16 and 16, this is the papers that we contribute so far. This is Scopus journal in Journal of Communication. This is performance of this is electronics journal, SSI journal in electronics, MDPI. This contribution based on the simulation environment proposed by this second paper, this SSI indexed paper, which were previously done, which do not consider a machine learning approach. So that we used to collect the frame size, system throughput pattern from that experiment simulation environment conducted by this. So frame size and system throughput. What is frame size? This represents average offered traffic load generated in the system by employing different traffic models. Here, we're going to adopt different traffic models, which is proposed in 15, such as Pareto, Veblen, and fractional Brown motion. The system throughput is defined as average system data rate at which the AP can successfully transmitted to all receiving stations, so that the collected pattern contained, this collected pattern, frame size and system throughput patterns contain knowledge about the effect of traffic pattern, channel condition, and number of stations. So the formation of frame size optimization problem, in the frame size optimization problem, the throughput THR is a complex function of frame size under the effect of channel condition, traffic pattern, and number of stations. Mathematically, we try to define it like this. So throughput is a function of the frame size, which is affected by these three conditions. Therefore, how the throughput can be maximized by optimizing the frame sizes, the main focus of the problem in this study. So neural network is adopted to build the knowledge and accurately model the throughput as a function with respect to the frame size. So the local information, the local maximum, the throughput function, throughput function can be found by adaptively adjusting the frame size using gradient ascendant by taking steps that are proportional to the gradient. Suppose at the end time of adjustment, the frame size was FRN, the throughput, the corresponding throughput was THR N. At the next time of adjustment, the frame size FRM is set as follow, mathematically as follows. So this is the next time of adjustment. The frame size will be the frame size plus change of the frame size will be added. This change of frame size depends on the gradient estimated throughput with respect to the frame size. Mathematically, it's expressed at this. So the change of the frame size is computed with this formula, with this expression. So this mu sign is used to represent the variable adjustment rate, which is heuristically selected for different network scenarios. So the gradient information, this change of throughput, this change of frame size is calculated or computed in this way. The mathematical expression of the detail of this mathematical expression is presented on the paper. Sorry, I didn't include in this slide. So anyways, the gradient, this change of throughput, change of frame size that we used to adaptively adjust the frame size expressed with this equation. So to cope with the effect of time varying channel condition and heterogeneous traffic patterns, online machine learning strategies adopted to achieve the data collection, knowledge building, and frame size adjustment kept online. So by allowing this online machine learning approach, we can able to keep the learning on fly after being deploying as new data arrivals. So the training data set is collected once every 50 seconds. The 50 samples will be collected for each training in considering different network scenarios, such as channel condition, traffic patterns, and number of stations to train the neural network. The ML, the machine learning approach, consists of one hidden layer with 4 neurons and output layer. So the back propagation only consists of 2 passes, forward pass and backward pass. So graphically, this is a model of the ML approach. So this flowchart represents the proposed machine learning approach consisting of the training pass. The training pass used to depict the derivation of the local gradient and the gradient for frame size adjustment. We use this. We add this training pass training pass procedure to make the frame size adjustment to perform the frame size, the proposed frame size adjustment based on the gradient information obtained from the neural network after the neural network is performed. So this is the overall diagram. What the element consists element in the proposed ML approach. We have the data set, frame size throughput pattern, that is the instant learning data set provided to the neural network. Once the neural network, once the training is conducted by the neural network, the knowledge is built with throughputs, which provide the throughput which provide the accurate throughput model with respect to the frame size. So the gradient information found from this neural network will be adopted by this training pass procedure to make the frame size adjustment. And then finally, or the record optimal frame size corresponding throughputs to illustrate the results. So here we can see some of the results in discussion for a performance under the effect of various traffic models. We can see the performance of our proposed machine learning approach under the effect of different traffic models. See here we have Pareto traffic model, Webview traffic model, and FBBM traffic model, fractional Brown motion traffic model, and their performance with respect to system throughputs. So here, the blue one is baseline approach, which is a FIFO approach, which does not consider adaptive aggregation approach. And whereas this is a maximum throughput, which this represents our previous work that provides the maximum throughput performance, throughput performance, but doesn't consider machine learning optimization approach. This one is our proposed machine learning approach. So here we can see the performance. If we see the system throughput performance of a proposed approach, it can achieve the maximum 500 megabit per second in parity traffic. When it compares with the baseline FIFO approach, it outperforms the performance of maximum throughput. So which is almost close to the maximum throughput achieved from our previous contribution, which does not concern machine learning approach to provide a maximum system throughput performance. We see WeBlue traffic. In the WeBlue traffic model, we also see the maximum performance of around 850 megabit per second is achieved by our proposed approach as compared to WeBlue traffic. In Pareto, WeBlue traffic model and WeBlue traffic model, our proposed approach provide maximum performance, means it is more which is more comfortable with this traffic model, that our proposed approach provide the maximum performance at above 800 megabit per second. Still, in this WeBlue traffic model, Pareto VM traffic model is the least performance. So our proposed approach is at maximum performance, which is closest to the maximum throughput of our previous contribution. Same with fractional power motion, but in fractional power motion achieve better performance that of Pareto traffic model. So in general, this representation illustrates that the traffic patterns in the network affects the system throughput performance. So this is the main point that we're going to demonstrate in this experiment. So the other one is the performance of our proposed approach impacted by channel condition. Here, basically, these are the comparative approaches, average system throughput performance achieved by different traffic models. These are the data. Same with under the impact of channel condition. Here we can see we have this is the average system throughput performance achieved in different traffic models. In Pareto, we believe in FBM traffic models for baseline FIFO, maximum throughput, and proposed ML approach, different channel condition. The least SNR 3 dB and the maximum 20 dB. So if we see the results here, Pareto traffic model in different traffic scenario, 3 is with the worst channel condition, 20 is the most ideal channel condition, it's good channel condition. So the maximum performance is achieved in all traffic model in 20 dB channel condition, because the channel is almost near to ideal, so the maximum throughput performance can be achieved. However, when we see, if we see in WeBlue traffic model, even under the same channel condition of 20 dB, WeBlue traffic model achieved the maximum 800 megabit per second. If we compare with Pareto, the maximum performance in 20 megabit dB scenario is 700. So when we see the list, so this illustrates that the channel conditions, the system throughput performance of the system throughput performance is also affected by the channel condition as well as the traffic patterns in the network. So here, WeBlue is achieve the maximum performance in all situations. So that's why maybe it means WeBlue traffic model is more suitable for models than that of Pareto. So basically, in Pareto traffic model, the traffic scenario is very breasty than that of fractional power model, than that of FBM in WeBlue traffic model. So the other one is performance of system throughput versus optimal frame size. Here we see the optimal frame size achieved in the obtained from different traffic models. As we see, when the optimal frame size at the optimal frame size, the maximum throughput performance achieved by WeBlue traffic models is almost 900 megabit per second at the optimal frame size of 1 megabyte. So this is a maximum performance. As you go with the optimal frame size, the throughput increases, whereas the baseline FIFO approach is the least performance here. So we see, if we see in Pareto traffic model, so the maximum throughput performance is achieved at 800 megabit per second with optimal frame size of 1 megabit per second. So which is the least performance out of WeBlue. And of course, FBM traffic model is achieved the worst performance here. Again, in fractional Brown, we see that our proposed approach achieved the maximum performance with increasing effects of optimal frame size. So this optimal with 0.93 megabit per second, the performance of our proposed approach achieved The system throughput performance that our proposed approach achieved is around 850 megabit per second. So this illustrates that the maximum performance achieved in different traffic models it depends on the traffic scenario in the network. So as a conclusion, in this paper, the machine learning-based adaptive approach is proposed that can optimize the frame size to maximize WLAN system throughput in the MU-MIMO channel. The access point perform the maximum system throughput measurement from this approach. For this approach, it collects frame size, system throughput pattern, which contain knowledge about the effect of traffic condition, channel condition, and number of stations. The proposed approach uses neural network to correctly model the system throughput as a function of system frame size. And after training the neural network, gradient information is used to adjust the system frame size that maximizes the system throughput. Finally, formation of the proposed ML approach is evaluated over FIFO aggregation algorithm under effect of heterogeneous traffic demand for VoIP and video traffic model. Basically, we consider VoIP and 50% VoIP, 50% video traffic application, channel conditions, and number of stations. Future work, this work do not, we want to extend this work to be conducted on real traffic scenarios. We want to extend this work in considering delay and the effect in different channel models such as relay and China on both uplink and downlink channel. Here we consider only the downlink channel. So these are the contributors. This is Lemlem Kassav, me, Dr. Jianhua Ding, Professor Mark Ding, and Professor Mortives and Professor Tai. If you have any question, you are welcome.